Article 430.24 of the National Electrical Code, or NEC, addresses the sizing of feeder conductors that supply power to multiple motors. The general rule outlined in 430.24 states that the feeder conductor must have an ampacity equal to or greater than 125% of the full load current rating of the largest motor in the group, plus the sum of the full load currents of all other motors in the group. This 125% factor for the largest motor is in place to account for the higher current draw that occurs during motor starting, as well as potential overload conditions. Motors draw significantly more current when they start, sometimes several times their full load current. This inrush of current can cause voltage drops and overheating if the feeder conductors are not adequately sized. The 125% factor provides a safety margin to handle these temporary overloads. However, there are exceptions in specific circumstances where a reduced percentage can be applied. One such scenario arises when dealing with motors that are unlikely to start or operate simultaneously. In these cases, the NEC permits a reduction in the required feeder conductor size. Instead of using 125% of the largest motor's full load current, a calculation using 25% of the combined full load currents of the other motors is allowed, in addition to the 125% of the largest motor. This allowance is based on the understanding that the probability of all the smaller motors starting or operating at their peak load simultaneously with the largest motor is low. Therefore, the feeder conductors do not need to be sized to handle the absolute worst-case scenario of all motors operating at full capacity concurrently. To illustrate this concept, let's consider an example with 3 motors: a 40 horsepower motor, a 150 horsepower motor, and a 10 horsepower motor, all operating at 460 volts. First, determine if all motors are likely to start or operate at the same time. If not, you can proceed with the reduced percentage calculation. Next, find the full load current, or FLC, for each motor. You'll need to consult NEC tables, specifically Table 430.250, to find the corresponding full load current values for each motor size at 460 volts. For a 40 horsepower motor at 460 volts, the FLC is approximately 52 amps. For a 150 horsepower motor at 460 volts, the FLC is approximately 192 amps. For a 10 horsepower motor at 460 volts, the FLC is approximately 14 amps. Now, identify the largest motor, which in this case is the 150 horsepower motor with a full load current of 192 amps. Calculate 125% of the largest motor's full load current. 1.25 multiplied by 192 amps equals 240 amps. Next, sum the full load currents of all the other motors. That's the 40 horsepower motor at 52 amps plus the 10 horsepower motor at 14 amps, which equals 66 amps. Calculate 25% of this combined full load current of the smaller motors. 0.25 multiplied by 66 amps equals 16.5 amps. Finally, add the two results together: the 125% of the largest motor's full load current and the 25% of the combined full load currents of the other motors. That is 240 amps plus 16.5 amps, which equals 256.5 amps. Therefore, the minimum ampacity required for the feeder conductor in this scenario would be 256.5 amps. Keep in mind that this is a simplified example and the actual feeder conductor size may need to be larger based on other factors such as voltage drop, ambient temperature, and the type of conductor insulation. Always consult the NEC and local electrical codes for specific requirements and guidance. It's also crucial to consider the application and operating characteristics of the motors when determining whether they are likely to start or operate simultaneously. Factors such as the type of load, the control system, and the operating sequence can all influence the likelihood of simultaneous operation. If there is any doubt, it's always best to err on the side of caution and size the feeder conductors based on the 125% rule for all motors. Additionally, the The overcurrent protection for the feeder conductors must be sized appropriately to protect the conductors from overload and short-circuit conditions. The overcurrent protection device, such as a circuit breaker or fuses, should be sized no larger than the ampacity of the feeder conductors, unless specific exceptions apply. Article 430 provides detailed guidance on the selection and sizing of overcurrent protection devices for motor circuits. Remember to always consult the latest edition of the NEC and local electrical codes for the most up-to-date requirements and regulations. Electrical codes are constantly evolving to reflect new technologies and safety standards, so it's essential to stay informed. Engaging a qualified electrician or electrical engineer is highly recommended for any electrical work, especially when dealing with motor circuits and feeder conductors. These professionals have the knowledge and experience to ensure that the electrical system is installed safely and in compliance with all applicable codes and regulations. They can also perform calculations to determine the appropriate conductor sizes, overcurrent protection, and other components for the specific application. In summary, understanding the difference between using 125% and 25% when sizing feeder conductors for multiple motors is crucial for ensuring the safe and reliable operation of electrical systems. The 125% rule applies when motors are likely to start or operate simultaneously, while the reduced percentage calculation is permitted when simultaneous operation is unlikely. Always consult the NEC and local electrical codes for specific requirements and seek the assistance of qualified professionals when necessary. NEC Table 430.24 provides the guidelines for sizing feeder conductors when supplying several motors. It states to sum the full load current of all motors plus 125% of the largest motor full load current. The question asks about sizing a feeder conductor for multiple motors unlikely to start or operate simultaneously. In these cases, the NEC allows for a reduction. The feeder conductor size can be reduced to 125% of the largest motor full load current plus 25% of the combined full load currents of all other motors. The reduction to 25% accounts for the low likelihood of simultaneous starting or operating currents of the smaller motors with the largest one. The feeder conductor does not need to be sized for the full 125% overload condition of all motors. Consider 3 motors of 40 horsepower, a 150 horsepower, and a 10 horsepower. The total full load current is 40 plus 150 plus 10, which equals 200 horsepower. The largest motor is 150 horsepower. The minimum size feeder conductor calculation is as follows. Firstly, calculate 125% of the largest motor's full load current, so 1.25 times 150 horsepower equals 187.5 horsepower. Secondly, calculate 25% of the combined full load currents of all other motors, so 0.25 times 50 horsepower equals 12.5 horsepower. Thirdly, add the two results, 187.5 horsepower plus 12.5 horsepower to equal 200 horsepower. Thus, the minimum size feeder conductor is 200 horsepower. It is important to use nameplate horsepower to calculate full load amps from NEC tables. Always refer to the specific NEC tables for motor full load currents based on voltage and motor type.